Welcome to EPG Pathshala lectures on numerical methods. This is module on eigenvalues and eigenvectors of real matrices. The eigenvalues and eigenvectors play very important role in many scientific and engineering applications. In the last modules 12 to 15, we have seen the methods for solving systems of linear equations. In the process, we have introduced matrices, and we have seen that the matrix theory plays an important role in understanding these methods. Yet another important concept in matrix theory is that of eigenvalues and eigenvectors, which has wide range of applications in science and engineering. Eigenvalues and eigenvectors play a significant role in study of differential integral equations, then in computing analytical solutions of nth order differential equations, linear systems of ODEs, integral equations, as well as stability analysis of solutions of systems of linear equations, finite difference schemes used for computing numerical solutions of such equations. Determining eigenvalue and eigenvectors for given matrix A is called as eigenvalue problem. So, let Aij, what are eigenvalues and eigenvectors of a matrix, that we will discuss here. So, let A be equal to Aij, be a real n cross n matrix. Aij's are the elements of the matrix A. A complex number lambda is said to be an eigenvalue of the characteristic or eigenvalue, or equivalently we call them as characteristic value or latent root of the matrix A. If there exists a non-zero vector x bar such that A x bar equal to lambda x bar, and the vector x bar is said to be the eigenvector of or the characteristic vector of the corresponding eigenvalue lambda. So, if the equation A x bar equal to lambda x bar is satisfied, then lambda is called as an eigenvalue of A and x bar is called as eigenvector of A corresponding to eigenvalue lambda. The condition that A x bar equal to lambda x bar is equivalent, if I transfer this on the other side and use matrix theory, then I can say that it is equivalent to saying that A minus lambda into I n cross n, that is identity matrix of order n, whole multiplied by the vector x bar, that is equal to 0. So, which is a homogeneous system of n linear equations in n unknown components of the vector x bar. So, unknown components of the vector x bar, and this is a homogeneous system because right hand side vector is 0 bar here. Thus, lambda is an eigenvalue of the matrix A if above system has a non-trivial solution, because we want a vector x bar to be non-zero, and therefore, this system, if this system has a non-trivial or non-zero solution x bar, then lambda will become an eigenvalue of the matrix A. Note that any homogeneous system always has a trivial solution. If I take x bar equal to 0, this equation will be automatically satisfied, but we are not interested in trivial solution, we are interested in non-trivial solution. However, we have the following results in this context. So, regarding homogeneous systems, we have a well known result in mathematics, and that is given by a homogeneous system B y bar equal to 0, where B is a n by n real matrix, has a non-trivial solution if and only if B is a singular matrix. So, if B is a non-singular matrix, then there will be only trivial solution, but if B is non-singular, then it will have a non-trivial solution, that means non-zero solution. So, for the proof of this theorem, you can refer to the books given in our additional reference material, reference number 2. It is well known that any n cross n matrix B is singular if and only if its determinant B is equal to 0. Again, concept of determinant, the definition and The other properties of determinant we can refer to 13, that is the Kreyszig book on engineering mathematics. Accordingly, the lambda, so now we are expanding this particular system in a proper form. So, we will say that accordingly the lambda is an eigenvalue of A if and only if the matrix A minus lambda I is singular. So, matrix A minus lambda I singular is equivalent to saying that determinant of A minus lambda I is equal to 0, and the determinant of A minus lambda I will be written in this format, because A minus lambda by I. So, from the diagonal elements lambda will be subtracted, that is it, and the remaining coefficients are same as coefficients of matrix A, and that will be equal to 0. So, this equation is gives us nth degree polynomial equation in lambda with real coefficients, and this equation is said to be the characteristic equation of A, characteristic equation of A. So, we can go back and see here that we said that your lambda is an eigenvalue if this system of equation, that is this system of equation, has a non-trivial solution. Now, this system of equation has a non-trivial solution by a known result here if and only if the matrix this is singular, that means A minus lambda I is singular matrix, and because if it is now this additional thing regarding determinant says that matrix is singular if and only determinant is equal to 0. Using that, I am saying here that lambda is an eigenvalue of A if and only if this determinant of this A minus lambda I is 0, and that gives me the characteristic equation of the matrix A. So, the fundamental theorem of algebra states that a polynomial equation of degree n greater than or equal to 1 with real coefficients has at least one real or complex root. So, this is your statement of the fundamental theorem of algebra, which can be referred in reference to. This theorem and other relevant results in mathematics lead to the following facts regarding the eigenvalues of a real matrix A. We are going to state number of results here, because these results are going to be used in discussing the numerical methods for solving eigenvalue problem. All the results stated here, we are not going to give the proof, but for some simple results we will give some outline of the proof also. So, the first fact about eigenvalues is that because of this theorem we can say that every real matrix A has at least one real or complex eigenvalue, because it is a algebraic equation, polynomial equation of degree n greater than or equal to 1. Characteristic equation is a polynomial equation of degree n greater than or equal to 1, and therefore, it has at least one solution, and that is your at least one eigenvalue of this. Then every real n cross n matrix A has exactly n eigenvalues which may or may not be distinct. So, every nth degree polynomial equation has n roots, and therefore, with real coefficient has n roots, and therefore, we are saying here that the characteristic equation will also have n roots, and these n roots are the nothing but the eigenvalues of matrix A. Therefore, matrix A has exactly n eigenvalues which may or may not be distinct, because some roots may be repeated. And so, if we are saying here that if lambda 1, lambda 2, lambda r less than n are distinct eigenvalues of A, then characteristic equation of A can be expressed in the form like this. So, some of these values may be repeated, this lambda 1 is repeated m 1 times, lambda 2 is repeated m 2 times, and m r times, such that sum of all this has to be equal to n. So, in this case m I is called the algebraic multiplicity of lambda I. So, if my characteristic equation is written in this form, and if lambda 1 is a root of this characteristic equation which is repeated m 1 times, then m 1 is called the algebraic multiplicity of lambda 1, and similarly m I will be called algebraic multiplicity of lambda I for all I equal to 1 to 3 up to r. So, if lambda is a complex not real, then eigenvalue of complex eigenvalue of a real matrix A, then lambda star, that is conjugate of lambda, is also conjugate of lambda is also an eigenvalue of A, and this is because complex root of a polynomial equation, again this is from matrix theory of equations, we can say that complex roots of a polynomial equations with real coefficients always occur in conjugate pair, and therefore, if lambda is a eigenvalue of A, the lambda star is also a root of the characteristic equation, and hence it is an eigenvalue of A. So, therefore, if n is odd, now if so whenever there are complex eigenvalues, they are bound to be in pairs, and therefore, if n is of degree odd degree actually, then it must have at least one real eigenvalue. So, since determinant of any n cross n matrix is same as that of its transpose A transpose, and when you are taking, you know that A transpose means matrix, you are changing rows into columns and columns into rows actually. So, in the process the diagonal elements will remain unchanged, and therefore, the characteristic equation of A and A transpose are bound to be same, and hence the A and A transpose will have the same eigenvalues. Now, this fact is very simple, which can be verified easily. The next one is that if x bar is an eigenvector of A corresponding to an eigenvalue lambda, then any multiple of x bar, so scalar multiple of x bar, so k x bar with any scalar k not equal to 0, k should not be equal to 0, will be also an eigenvector of A corresponding to lambda, and this can be seen very easily like this. This follows from the fact this, if lambda is an eigenvalue, this equation is set, and x bar is an eigenvector, then x bar will be equal to lambda x bar, but that will imply that for any scalar k I can multiply on both the sides, I will get k x bar equal to k into lambda x bar. Now, once I do that, this will imply that now because it is a scalar, we can say that A into k x bar, so k can be clubbed with x bar, and lambda we can take out, and k x bar can be written in this particular format. So, this will mean that lambda the k x bar is also an eigenvector of A corresponding to eigenvalue lambda. So, this leads to a very simple result here, that set of all eigenvectors, because see every multiple of an eigenvector is again an eigenvector. So, therefore, if we take set of all eigenvectors corresponding to an eigenvalue lambda of a real n cross n matrix A is a vector subspace of vector space C n, and over the field of complex number C, which is called the eigenspace of lambda, which is completely determined by finding the linearly independent eigenvectors of A, because every vector space has a basis, and the basis is formed by linearly independent vectors. So, if I can find out linearly independent vectors corresponding to lambda, all the linearly independent vectors, then that will give me the basis of the eigenspace over here. So, the number of linearly independent eigenvectors associated with an eigenvalue lambda is called the geometric multiplicity of lambda. We have seen algebraic multiplicity as number of times that root lambda 1 is repeated in characteristic equation, and geometric multiplicity is that corresponding to lambda how many linearly independent vectors are there, that will decide the geometric multiplicity of A, which is usually denoted by small m lambda, and this is only because that it is well known fact of the mathematics that geometric multiplicity of lambda is always less than or equal to algebraic multiplicity of lambda. We are not going to prove any results as you already stated earlier, but we will see some of these results in the examples. So, the algebraic multiplicity of lambda is nothing but number of times that lambda 1 appears in the characteristic equation, and the geometric multiplicity of lambda is number of linearly independent eigenvectors corresponding to lambda. And it is well known fact of mathematics that geometric multiplicity of lambda is always less than or algebraic multiplicity of lambda. We will verify these facts by taking in simple examples. The following, we are considering three matrices of three illustrations here. So, the following matrices we are going to find all the eigenvalues, their corresponding eigenvectors, and determine the algebraic and geometric multiplicities. So, suppose I take matrix A1 to be like this, then its characteristic equation is just you have to subtract minus lambda in the diagonal elements and this equal to 0. When you solve this particular determinant, so if you compute this determinant, it will be 1 minus lambda cube minus 1 equal to 0, and therefore, I will get the equation as lambda into lambda square minus 3 lambda plus 3 equal to 0, and this equation very clearly has a root. First root, one root is 0 and another root is 3 plus I root 3 by 2. The quadratic equation has roots like that. So, 3 plus I root 3 by 2 and 3 minus I root 3 by 2. So, you can see that there are two complex roots and this is conjugate of this. So, therefore, conjugate pair of complex roots and one real root, because degree is odd here, there will be one real root. Now, to find eigenvectors corresponding to eigenvalues, what we have to do is we have to solve this system of equation A minus lambda I x bar equal to 0 bar. So, that means A minus lambda I, when I put lambda equal to 0, this will become original matrix A only into this equal to 0, and that is now if I take matrix multiplication, I will get x 1 minus x 3 equal to 0. This will give me minus x 2 plus or x 1 minus x 2 equal to 0, x 2 minus x 1 equal to 0, and this will give me minus x 2. So, x 3 minus x 2 equal to 0. So, that is what I will be getting. Now, these three together will give me x 1 equal to x 2 equal to x 3. Now, by so we have a choice of selecting x 1, x 2 or x 3, but all of them must be identical. So, suppose I take x 1 equal to 1, then the corresponding eigenvector will be 1 1 1, because all of them must be equal. So, eigenvector corresponding to lambda equal to 0 is 1 1 1. It can also be, as you know, we have seen that if I take x 1 equal to 2, it will be 2 2 2, scalar multiple of this. All scalar multiples of 1 1 1 are going to be the eigenvectors of A corresponding to lambda equal to 0, and we can also choose eigenvector with unit modulus by, you can divide by norm of this vector to all these elements, and I will get unit vector as the eigenvector of that. For lambda equal to 3 plus I root 3 by 2, the system will become this. Now, I am subtracting this from the diagonal elements are 1 1 1. So, 1 minus 3 my I root 2 by 2 will give me this values here. So, if I again take this matrix multiplication, I will be getting this x 1 minus x 3 equal to 0, or minus x 1 plus minus 1 minus I root 3 by 2 x 2 equal to 0, and minus x 2 plus the minus 1 minus I root 3 by 2 x 3 equal to 0. So, this is what I will get, and you can see that by if I select x 1 equal to 1, then I will be getting x 2 as 1 upon this, and by complexity I can say that it will be minus 1 plus I root 3 by 2, and x 3 I will get from here directly this value. So, x 1 equal to 1. So, x 3 will be equal to minus 1 minus I root 3 by 2. So, we can get this as eigenvector of this. Similarly, lambda equal to 3 minus I root 3, you can follow the same procedure and its eigenvector will be considering this. Note that this matrix has one real and two complex conjugate of each other eigenvalues, and eigenvectors corresponding to two complex eigenvalues are also conjugate of each other, because this vector is conjugate of this. Here there is a minus sign, here there is a plus sign, whereas here we have got a minus sign here and plus sign here. One is real, so conjugate of one is 1 itself. So, therefore, this is a conjugate of this. So, these facts we can verify here. The second example I am taking it as A 2 equal to 2 4 0 0 2 0 1 3 1. The characteristic equation of A 2 is given by this. Again you solve this eigenvector, this equation will be becoming like this, and by solving that I will be getting 2 2 1 as eigenvalues, and to find eigenvectors we have to solve this system for lambda equal to 2. So, if I solve this system for lambda equal to 2, I will get 4 x 2 equal to 0, 0 equal to 0, and x 1 plus x 3 minus x 1 plus 3 x 2 minus x 3 equal to 0. So, x 2 equal to 0 and x 1 will be equal to x 3, that will be my contention here, because x 2 equal to 0 will give me x 1 equal to x 3, and taking x 1 equal to 1, I will be getting vector as 1 0 1. Now, you can see that algebraic multiplicity of 2 is 2, because 2 is appearing 2 times. So, therefore, algebraic multiplicity is 2, and there is only one eigenvector corresponding to this eigenvalue 2, and therefore, I say that geometric multiplicity of this is 1. Then similarly, you can find for lambda 1, the corresponding eigenvector will be this, and algebraic and geometric multiplicities of this are this eigenvalue are going to be 1. For matrix A 3, you can see that this is a matrix A 3, which is very singular matrix. In fact, the characteristic equation A 3 is given by this, and that is we are getting lambda square into 1 minus lambda equal to 0. Therefore, eigenvalues are 0 0 and 1. When eigenvalues are 0 0 and 1, and if I take find eigenvectors corresponding to lambda equal to 0, I have to solve this system of equation. When I express this, so this will first equation will not give me anything, only identity I will get, and then this will give me x 2 equal to 0, and the third equation will give me x 3 equal to 0. So, we have a choice, freedom to choose values of x 1 and x 2. Both these equations are giving me x 3 equal to 0. So, this system has only one equation which is valid, and that is x 3 equal to 0. Therefore, I have a choice of selecting values of any values for x 1 and x 2. So, if we taking x 1 equal to 1 and x 2 equal to 0, the corresponding eigenvector will be 1 0 0, and taking x 1 equal to 0 and x 2 equal to 1, corresponding eigenvector will be equal to 0 1 0, corresponding to lambda equal to 0. So, lambda equal to 0 has two linearly independent eigenvectors associated with it, and therefore, algebraic multiplicity of lambda 0 is 1, algebraic multiplicity is 2, and geometric multiplicity is also 2. And then similarly, corresponding to lambda equal to 1, the corresponding eigenvector will be this, and both algebraic and geometric multiplicities are going to be 1. So, here we have seen an example of a vector of a matrix in which the eigenvector has algebraic multiplicity 2 and geometric multiplicity 1, and a matrix where both algebraic and geometric multiplicities are 2. Now, we are talking about relevance of eigenvalues and eigenvector value problem in the real world situation. So, we are giving here two illustrations. One illustration is regarding stability of solutions of the systems of linear equations. So, I am taking, as discussed in the module 12, many real world problems can be modeled into system of linear equations. In the process of modeling, number of simplifying assumptions are imposed. Also, measurements of process parameters are involved, and due to this, the coefficient matrix and right hand side vector of the system, that means which represents that model, which represent the mathematical model of the process, are prone to approximation errors and measurement uncertainties. In the solution of the system, it is sensitive. If the solution of the system is sensitive to such variation in the coefficient matrix or right hand side vector, then the conclusions drawn on the basis of the solution of such systems may not be reliable, because your model is inaccurate and your solutions are not very reliable or very sensitive to that inaccuracy, then the conclusions may not be reliable. And hence, it is essential to ensure that the solutions of the linear systems are stable relative to such small errors in the system parameters. The following example illustrates such a system of equations and role played by eigenvalues in determining such instability and modifying the system to yield stable solutions. In fact, we will not go into this part, but we will just see that how the instability can be represented in terms of eigenvalues and eigenvectors, and by controlling these eigenvalues eigenvectors we can make sure that the system becomes stable. So, consider a simple system I am taking 2 by 2 system, and therefore, I will not spend more time on solutions of this. You can verify these statements very easily. The solution of this system when you are talking about this is 3 1, and if the vector b bar is slightly perturbed. So, now instead of taking 3, I am taking 3.05, and instead of 1 I am taking 1.02. Suppose that actual measurements in the parameters are like this, and we are approximating it by this, which is a normal practice, and then you have what will happen to the solution? Solution of the system becomes 8 3. So, if this is real, then solution should be 3 1, and if this is real, then solution should be 8 3. Now, it is very difficult to say that when you are approximating, these two solutions are far off from each other, though the system parameters are not that far. So, linear system for which this happens are called badly conditioned or ill conditioned systems of equations, and this is ill conditioned, unstable with respect to right hand side vector b bar, because small changes in b bar has made the solutions far off from each other. This is a unstable in application, this is undesirable in applications, as in nearly all computations with real data there is an error due to rounding off or due to imperfect measurements, and in such systems the apparent solutions can be virtually meaningless. So, this is not desirable. This is another example of the similar system. Here now I am perturbing slightly a. So, my a is 100 minus 200 minus 200 401 x 1 x 2 equal to this. The solution will be given by 200 1 and 100. And if you suppose the elements of the coefficient matrix are slightly perturbed like this. So, instead of taking 401 here, I am taking 101 here and 400 here, and everything else remains same, then the solution becomes this. You can see that the solution is far off, whereas coefficient matrix is not that far. I mean, it is very close to each other, and therefore, again this is an instability here. So, thus in this case also the slight variation in matrix A results into huge variation in the solution. The reason seems to be the bad conditionality of the matrix A. A proper measure of bad conditionality of any n cross n matrix A is a condition number of A, which is defined in terms of matrix norm. Matrix norm can be just extended like norm in Rn. So, magnitude of the vector we are talking about. In the similar way, we can extend the matrix norms here. I am not going into the details of all this, but you can see from the literature all these facts. So, condition number I am defining it like this: if A is invertible, and infinity if A is singular. If A is an n cross n normal matrix, that is if A transpose A is equal to A transpose. In that case, the condition number can be represented in terms of eigenvalues, which are eigenvalues of matrix A. So, this eigenvalue is lambda x, lambda max and lambda min are respectively the maximum and minimum of the set of this. So, what is this set? This set is mod lambda, lambda is an eigenvalue of A. So, you take all eigenvalues, take their absolute values, and you consider the maximum of these absolute values and minimum of these absolute values, take their ratios, that will give me condition number. So, by determining maximum eigenvalue and minimum I mean this maximum and minimum absolute value eigenvalues, if I determine, I can find out what is the condition number, and if condition number is large, matrix is going to be unstable, condition number is small, matrix is likely to be stable. So, this is what will happen here. Thus, for checking stability of the solutions of the linear systems, one has to determine the condition number of A, for which it may be enough to determine the eigenvalues with largest and smallest absolute values. So, Markov analysis, this is another example we are talking about. I am talking about Markov analysis of market shares of companies. Many times you talk about market shares of various companies. Here I am taking a very theoretical or fictitious examples, only using some real names. So, consider a problem of determining a market share of Patanjali biscuits in a city. Suppose that a survey is carried out on 1000 citizens and they were asked a simple question that which brand biscuits they were using in the previous week and which brand of biscuits they are using in the current week. So, that is what we are trying to ask them, and as a result of this survey we get the following data. So, what data we have got? So, out of 1000 respondents, we are saying that 250 said that they are using Patanjali biscuits in the previous week they were using, and others were 750 people were using biscuits of other brands. During the week what happened is that Patanjali got gain of 75. So, 75 customers took Patanjali biscuits, but it also lost those who were using Patanjali biscuits. Out of that 50 have gone to other brands, and from other brands 50 from Patanjali it has come here, and the 75 that is gain. So, 75 from other brands have gone to Patanjali. So, this is what is happening, and therefore, the new variation in the distribution of customers using these biscuits will now become 275 and 725. We can use this and we can realize this even by using your or by applications of eigenvalues and eigenvector. Let us see that how we can do that. So, suppose that the customer behavior continues to be the same over a long period of time, that means the same behavior continues like this. Then what will be the market share of the Patanjali biscuits in the long run? So, that is what I want to find out. So, from the given data it is clear that the Patanjali retains 200 out of its 250 customers and loses 50 to other brands, and that is retains 80% of its customers and loses 20% to other brands. And similarly, other brand collectively retains 90% of their customers and lose 10% to the Patanjali, and hence this is called as transition matrix of probabilities, actually transition probabilities or matrix of transition probabilities. So, what does that mean? That those who are using Patanjali biscuits, they will continue to use Patanjali biscuits with probability 0.8 and will move to other brands with probability 0.2. And similarly, those who are using other brand biscuits, they are likely to go to Patanjali by with probability 0.1 and they will continue with other brands with probability 0.9. So, this is what is happening called as transition matrix. So, if I take M transpose, the transpose of this transition matrix M can be used to compute the market share of Patanjali in this week from its share in the previous week as follows. How we are going to do is this. Note that from the given data, the previous week's status of the market share is represented by this, because 250 and 750. So, 25% were or customers were using Patanjali brand and others were using this. So, therefore, these are the probabilities that any selected any customer, he will be using Patanjali brand of biscuits with 0.25% probability and 0.75% probability. Then current week's status is given by what? So, you multiply, take this transition probability matrix and multiply by this initial share of market, and then you get the new share of market. This is what 275 and 725, this is what we got in our first table. 275 and 725 divided by 1000 will give you that, those probabilities. So, we get this, and in the long run, if I want to find out, now to determine the market share in the long run, it is required to find an equilibrium market share. What do you mean by equilibrium market share? Which once reached remains fixed. That is, we have to find out a vector x bar such that M transpose x bar is x bar. So, if M transpose x bar is x bar, if I want to find out that, then since this is your M, now you can this is what I want to find out, but what is that exactly? Look at this now. Since you know that this into this 1 1 if I take, then 0.2 into 0.2 0.8 plus 0.2 will be 1 again. So, 1 will be like that. So, 1 is an eigenvalue of matrix M, this is matrix M. So, I can say that 1 is an eigenvalue of matrix M and hence that of M transpose also. And thus, problem of finding out M transpose x bar equal to x bar is same as saying that it is problem of finding out market share of Patanjali biscuits to finding eigenvectors of M transpose corresponding to the eigenvalues 1, which is obtained by solving the system of equations like this. If you solve this system of equation, which will yield x 1 equal to 1 by 3 and x 2 equal to 2 by 3, and therefore, we conclude that the market share of Patanjali biscuits in the long run will be 33.33%. Now, we are talking about some results on eigenvalues and eigenvectors of special matrices. As stated earlier, for any real matrix A, the eigenvalues of A could be real or a complex number corresponding to one eigenvalue. There could be one or more linearly independent eigenvectors, thus it makes it difficult to solve the eigenvalue problem. However, in certain special cases, there are good results in mathematics which help designing some efficient numerical methods for solving this eigenvalue problem. A good account of some of such results is given in references 13. Some of these results which are relevant to for our purpose are stated here. We are going to state these results and some of them will just try to verify below, and one may refer 13 for the simple proofs of these results. So, you can look at those references here. Definition 4.1, a real n by n matrix A is said to be symmetric if A is equal to A transpose. Now, the first result says that eigenvalues of a real symmetric matrix are always real. Second says that if n cross n matrix A has n distinct eigenvalues, then A has a big basis of eigenvectors x 1, x 2, x 3, x n for R n. So, all the eigenvectors here will be linearly independent, that is what it would mean. So, if n distinct eigenvalues will yield me n distinct linearly independent vectors. What we will see here is, suppose you have got two distinct eigenvalues, then corresponding vectors should be linearly independent, and that I am trying to show you here, that if lambda 1, lambda 2 are distinct eigenvalues of A and x 1, x 2 bar are the corresponding eigenvectors, it is easy to see that x 1 and x 2 bar are linearly independent. Suppose they are not, then x 2 bar will be multiple of x 1 bar, and therefore, we will get here for some k not equal to 0, lambda 2 into k x 1 bar will be same as lambda 2 x 2 bar, because k x 1 bar is x 2 bar, but lambda 2 x 2 bar is a x 2 bar, because it is an eigenvector corresponding to lambda 2, and again I will write k x 2 bar, I can write it as k x 1 bar. So, I can write it as k into a x 1 bar, and a x 1 bar is lambda 1 x 1 bar. So, I get this, from that I will get this equal to 0, but which is which contradicts. Why? Because neither lambda 2 and lambda 1 are equal, nor k equal to 0, nor x 1 equal to 0, and therefore, this contradicts, and therefore, we conclude that this cannot be possible, this is not possible, and therefore, they must be linearly independent. Now, theorem 3 says that a symmetric matrix has an orthonormal basis of eigenvectors for R n. So, what orthonormal basis means what? The eigenvectors are linearly independent, they are mutually orthogonal, that means their dot products of x I x j will be 0 for all I not equal to j, and their norms are going to be 1. Now, definition 2 says that n cross n matrix B is called similar to n cross n matrix A if B equal to P inverse A P. So, for some non-singular n cross n matrix P, so this should be non-singular matrix, then only P inverse will exist, and if this happens, I say that A and B are similar matrices. The transformation which transform matrix A into B like this is called as a similarity transformation. Similarity transformation play a very important role in math. Now, theorem in the context of eigenvalue eigenvector, we have got this theorem that if a matrix B is similar to matrix A, that is B equal to P inverse P A P for some non-singular n cross n matrix P, then B has same eigenvalues as that of A. And not only that, moreover, if x bar is an eigenvector of A, then y bar equal to P inverse x bar is an eigenvector of B, corresponding to the same eigenvalue. And you can see here that for if lambda is an eigenvalue of A and x bar is a corresponding eigenvector, then A x bar will be equal to lambda x bar, and therefore B y bar will be equal to B into P inverse x bar, which is equal to B P inverse x bar. Okay. But B P inverse is same as P inverse A, because B equal to P A P inverse. So, therefore, P inverse A x bar. Now, this will be P inverse A x bar will be lambda x bar. So, P inverse lambda into x bar. So, I can say that lambda outside and P inverse x bar, and that is lambda y bar. So, therefore, we will get the proof of simple proof of this results. And definition 4.3 says that an n cross n matrix B is called as an orthogonal matrix if A transpose equal to A inverse. And for orthogonal matrix, there is a special property that if this is an orthogonal matrix, if and only if all its column vectors form an orthonormal basis of R n, because there will be n orthonormal column vectors. If all these n column vectors form an orthonormal basis, means they are mutually orthogonal to each other, and C I C j, that means this should be equal to 1. And we have got a this theorem which says that if an n cross n matrix A and eigenvectors this form a basis of R n, then I can diagonalize the matrix like this. So, D equal to x inverse x A, where x is a matrix with the eigenvectors as column vectors, because we have got eigenvectors form a basis. So, I can form a matrix of taking these eigenvectors as column vectors. That matrix I am calling it as a capital X, because they are orthogonal, x inverse will exist. X inverse A x if I take, then that will be resulting into a diagonal matrix, and with all eigenvalues as diagonal entries. And therefore, in this case, if A is in this case when A is symmetric, D will be equal to x transpose A x, because if A is symmetric, we will get x transpose A x like that. Okay. So, we will get here in case when A is symmetric, we get D equal to x transpose, because x inverse will be same as x transpose here. So, outline of some of these results are given above. However, proofs of some of these results are difficult and refer to the relevant references. We can take an example which will illustrate some of these results. So, consider a matrix. You can see that this matrix is symmetric matrix, because you can see that these elements are same. So, lower diagonal elements and upper diagonal elements are same. So, A equal to A transpose, therefore, it is a symmetric matrix. Find the eigenvalues and the corresponding eigenvectors of this matrix, and we will try to see diagonalize matrix, diagonalizable matrix. So, we will diagonalize the matrix A. So, what we are observe that A is symmetric. The characteristic equation of A is this. So, if you solve that equation, I will get this equation. Solving this, we will get eigenvalues as 2, 4, 10, that you can see verify. Then we find out eigenvectors corresponding to these eigenvalues. So, for lambda equal to 2, I will get again solving this system. We have already done this exercise earlier. So, I will not repeat that. So, we get a system like this, and from that taking we will get a non-trivial solution as 1 minus 1 0, and therefore, eigenvector corresponding to A eigenvalue 2 will be this. Similarly, eigenvectors of A corresponding to 4 and 10 are going to be like this, and if I take these 3 vectors together and divide by their magnitudes, I will get 3 vectors like this. You can see that all these 3 vectors are going to be orthogonal to each other, because if I take cross product of this 2, for example, this and this, a dot product of these 2, then it will be 1 minus 1, that will be 0, because 0 into minus 2 is 0. Similarly, I can take dot product of these 2, that will also be 0, and we will get here orthogonal eigenvectors, and their norms also will be equal to 1, and therefore, we can see that for a real symmetric matrix, there exists an orthonormal basis. This proof this is realized. Then if I take P equal to matrix of eigenvectors like this, and if you take this product P transpose A P, because it is symmetric matrix, we will get this P transpose A P, I will get this diagonalized matrix like this, and note that P is orthogonal matrix and diagonal entries of D are nothing but the eigenvalues of A. So, that is what we are going, this verifies theorem 4.6. So, these examples verify this theorem. So, in the summary we can say that in this module the important concept of eigenvalues and eigenvectors were introduced. Various properties of eigenvalues, eigenvectors of real n cross n matrix were discussed along with relevant illustrations. Two real world applications of eigenvalues, eigenvectors were discussed to emphasize the relevance of eigenvalues, eigenvectors, and in the end some important results on eigenvalues and eigenvectors for special matrices were discussed. These results will be used in designing efficient numerical methods for solving eigenvalue problem. Thank you.